Okay, number 83. At one point on the curve is y equal to the natural log of x plus 4, and then parentheses to the power of 2 squared. Is the tangent horizontal? Okay, so first of all, let's graph what this is, see what it looks like. So I'm going to go over to y equals Desmos. I love using Desmos, it's free. Do a pretty good job of graphing most things. Y equals Desmos. Okay, so I have the function y equals 2, and it's bracket ln of x plus 4, I think, close parentheses, bracket to the power of 2. Is that it? Here it is. Ln x plus 4 squared. Okay. So here's my function, right? And I want to find out when the tangent is horizontal, right? So already from the graph, I can get a pretty good idea of when that is. Remember that, let's go over here. I need, what do I want to do? Let's put it down here. Remember that the equation of a line, when we want to work with a line, we have a couple of equations. Y equals mx plus b is one form of a line. And then the other one is going to be y minus y subgiven equals to m, the slope, times x minus x subgiven. Right? So if we know m, the slope, and one point, x sub given, comma, y sub given, right? Some little point that we know, then we can plug it into there, and get the equation of the line. Good? Okay. Well, if we have this function, and I'm just going to do I'm just going to murder this with this ugly looking thing, whatever it is, it does this kind of thing, goes that way, whatever. We know that the tangent line at a particular point, let's say that's the point right there. Let's say I pick some value a, then that output there is going to be f of a. So that point right there is going to be the point a, comma, f of a. Right? Okay, and then the slope of the line tangent at that point, whatever that is, right, it's going to be something there. The slope, well, it's going to be given by the function f prime evaluated at a. Right? The derivative of that function is an equation that produces the slope of the line's tangent at that line. Good? Okay. So we know the slope is going to be f. So for us, in this case, we know the slope m is going to be equal to f prime at a at point a comma f of a. Okay, so using all that information, I have that the equation of the tangent line is going to be equal to y minus f of a equals to f prime of a times x minus a. Right? This is going to be the equation of the line tangent. This is the equation of line tangent to f of x at x equals to a. Good. So I want to use this little formula we just came up with to put it on my my graph so that I can visually see that. Okay, so I'm just going to come over here and I'm going to rewrite this as f of x. Nice and convenient, like that. So now I have f of x equals to that, right? So then I can create a slider a, so that a equals to, let's put a comma f of a, and then I'll create this as a little slider. So notice what this is. So see this little slider here? That means that I'm I'm allowing a to be negative 0.8 there, so there's negative 0.8, and then it's graphing that ordered pair. I can label it as well. So I can go slide back and forth and find it. And you know what? I'm going to change the color since I usually like to put red as my tangent. So let's put this in blue, and let's put this guy in red, and let's put it in purple. Okay, there we go. So there. So the little purple dot traveling along the curvature f of x. Good. Okay, and now we're going to type in that equation we found for the tangent line. Y minus f of a equals to the slope, which is f prime of x, of a, times x minus a. And let's make it red. I like my tangent lines to be red. Done. Okay, so what we have here is that the original function is that blue one, and then this red one is the tangent one, and now as I move across the function, you can see where that tangent function is going. Right, so here it's got a really big negative slope, that tangent one, and then it kind of curves around that little edge there, and then it turns into a positive slope. And we can see the motion of that. Maybe if I zoom out, it might be a little bit easier to move this around. So there we go. Okay, so we have an equation of the tangent line. And then, okay, so back to this question. It was asking, when is the tangent line going to have a slope that's equal to 0, right? Because it's asking us when is it going to be horizontal. Okay, going back to this question, number 80. Here it is. At what point on the curvature is the tangent horizontal? Horizontal means that it matches the x-axis, right, the horizon, which means that the slope is equal to 0. So from just doing this, it looks like that's the answer, right? X equals to negative 3 should be my answer from just based on this, right? So then we can do some work and make sure it matches, right? This is not good enough as an answer yet. I'm just giving you a nice visual of what we're looking for. Okay, all right, so let's do some actual work. We need to find the derivative of this thing. So we have that y equals to bracket ln of x plus 4 bracket squared, and we need to find d dx of y, which is going to be d dx of this thing, ln x plus 4 close squared. Good. So this is going to be equal to 2 ln of x plus 4 to the power of 1. Right? We pretend this is just one big variable, like a giant x, and we note that if this was just one variable, say u squared, the derivative with respect to u, this thing, is just equal to 2u to the first power. So that's what we do here. Bring down the 2, the derivative, this stays the same, power of 1. But now we have to multiply times the derivative of the inside part, right? Times the derivative with respect to x of the inside part, which is just going to be ln of x plus 4, right? That's what the chain rule tells us. Good. So this would be 2. Now, to the power of 1 doesn't really do anything, so just put 2 times ln of x plus 4 times, and now the derivative of this. Again, if this was just one simple little letter, it would be ln of x, and we know its derivative would be 1 over x. So the derivative of this is going to be 1 over x plus 4 times the derivative of the inside part. Again, chain rule. Is that okay?
Gotcha.
Good, good, good. Okay, and then finally, the derivative of this, d dx, the derivative of this is just going to be equal to 1. So we'll end up with 2 ln of x plus 4 times 1 over x plus 4 times 1.
Perfect.
Good, good, good. Okay, so now that's the equation of the derivative. We just have to figure out when that derivative is going to be equal to 0.
Okay, that's where the problem started.
Okay, so far we have that dy dx equals this, and there's not a great way to simplify it, so we end up with 2 ln of x plus 4 all over x plus 4, and we want to find out the value of x such that this derivative equals to 0. Find x such that the derivative equals 0. 2 ln of x plus 4 over x plus 4 equals to 0. Okay, whenever we have a fraction and we want to find out when it's 0, then what we could do is just figure out when the numerator is 0. Right? A fraction is 0, a over b equals to 0 when a equals 0, and b is not 0. That's what we want. Anything where the numerator is 0 and the denominator is not 0. So as long as my answer is not -4, I'm okay. Right? Because -4 would make the denominator 0. So I just need to reduce it to figure out this. When is this part equal to 0? Okay, we'll divide both sides by 2. By 2, by 2. And we end up with ln of x plus 4 equals 0. Right? And to figure this out, let's raise both sides power of e to the power of ln x plus 4 equals to e to the power of 0. Right? E to the power of 0 is just going to be equal to 1. Okay. E to the power of ln, these two undo each other. They're inverse functions. So we just end up with x plus 4 better be equal to 1. So x equals to -3. Which matches what we thought in our picture. Right? So we have the x coordinate. To find the y coordinate, we got to come back to our function and plug in a -3.
I always have a lot of trouble with the E thing. I don't know why. I get it, but I don't. Does that make sense?
Sure, it's an unusual thing, so something you got to practice. In chapter 3, I think, is when it's introduced.
Yeah. Yeah, I can do them, but they don't. It doesn't make sense to me. So that's something I will have to cover in your office hours. I don't want to hold up the class.
Okay, sounds great. Okay, so now we still have to find y. So we go back to our definition of the function up here, which was... No, stop it. Y, where are you? Oh, y. So y was equal to, from here, our original statement was y was equal to ln of x plus 4 squared. And now we want to know what happens when x equals to -3. So y equals to ln of plus 4, the whole thing squared. And we're going to plug in a -3 right into here. So we end up with ln of 1. Ln of 1 squared equals y. Squared equals y. Ln of 1 is 0. So this becomes 0 squared. So y equals to 0. And we have our ordered pair. Right, so it matches our picture. When we graph this thing did this weird thing where it came this way and like went that way or something like that. And that point right there is exactly what we discovered. That at this point right in there, the tangent line is going to be horizontal. It's going to match like this, like that, right there at that point. And at that point, we have the ordered pairs -3, 0. Right? So it matches this thing. right there, negative 3 comma 0. Good. Questions, 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 questions? Okay, so for the other one, let's just do the first one and kind of get the ball rolling. Number... said number 87. Number 87 has an equation of motion of the form S equals to a e to the ct cosine of wt plus is that a phi? No, it's not phi. Omega. I forgot the name of that letter. Represents the damped oscillation of an object. Find the velocity and the oscillation of the object. Okay, so one thing that might be confusing is that they didn't really, the way that it's described, it's maybe not as clear what the independent variable is. There's so many letters running around, but it's the letter T, right? Very often, motion, velocity is connected to time. Therefore, we use T to represent the independent variable of our position function, right? And so hopefully you did some work in Calculus 1 where we realized that the first derivative of a motion function is the velocity of that object, whatever the object is, and that the second derivative is the acceleration of that object, right? So we just have to find the first and second derivatives of this thing. So let's see if I can. I'm gonna need a new sheet. Right, so they gave it to us as S, but instead I'm going to rewrite it as S of T, so it's clear that T is the independent variable, and I hate T because then it looks like a plus sign, so I might change it. But okay, so then we have a constant A times e to the negative ct times cosine of omega t plus, there we go. It's zeta. I don't know what it is. No, it's not zeta.
That's gamma, right?
Might be gamma. Yeah, maybe it's gamma. I don't know why I'm forgetting this. I have a terrible memory. That's why I chose to study math.
Yeah, me too. Sad. That's why I don't want to study math. My memory sucks.
What? No, math is perfect. You don't have to memorize very much. It's one of the sciences where you memorize the least. If you find yourself memorizing too many things, you're doing it wrong. Math should be derived from very simple ideas. Any rate, so here's the independent variable, right? In red, I highlighted it. That means everything else, this omega, this W, this gamma maybe, this C, this A, these are all constants. Good? Okay, so now we got to find derivatives. The first derivative of this function, well, we have a multiplication of two functions here. Forget this constant. We just have to deal with this. So this is going to be d dt of the entire thing, and I'll just do it step by step, although you don't have to do every little step, since I think if you can skip a couple of these steps, it might actually look a little nicer. But anyway, we have this multiplication. I'm going to bring out the constant, a times, and it's going to be the derivative of the first function, which is going to be e to the negative ct, times cosine of ut plus gamma, like that, plus, and now, remember we take turns, so now leave that function alone, times the derivative with respect to t of the other function, cosine wt plus gamma, like that. Right? So there are two functions here. There's this function and there is this function. and there's a multiplication, right? So the product rule tells us to take turns with it and then add the two. So I'm going to take the derivative of this one, multiply it by this function, plus, and then leave the first function alone, multiply times the derivative of the second function. And then this constant, since it's being multiplied, I can just pull it out in front and multiply the whole thing at the end by capital A. So it's going to be capital A times the derivative of this. The derivative of this is going to be e to the negative ct. That looks like an e there. Negative ct, right? The derivative of this function is to copy it again. It's going to be the same thing. Times, the chain rule tells us to multiply it times the derivative of the numerator. Right? Times cosine of t plus, good, plus, and now this, we leave this guy alone, times the derivative of this. The derivative of cosine is going to be negative sine t plus gamma times the derivative of the inside part once again, times the derivative with respect to t of t plus gamma. Okay, good. Okay, so then we'll have A be equal to negative c times cosine wt plus m plus e to the negative ct. And then, well, I should have put that minus. I'm going to put that minus out in front, which means I'll take out this subtraction and make it a minus, right, because of this guy. So subtraction. And then I have sine of wt plus gamma. And then the derivative of this with respect to t is just going to be times that. Good? Good. Okay. Well, I still have a minus here, so I guess I could factor out the minus. It depends on how you want to present the final answer. They both have a e to the negative ct term in common, so I can factor that out. They both have a cosine of this function. Oh no, sorry, that's a cosine, that's a sine. Never mind. Okay, so there's not much else I can do. I'm going to factor out a minus. I'm going to factor out the minus. I'm going to factor out this term and this term from both of them. And so I'll end up with a and then minus a e to the negative ct. And then inside here, I'll end up with c. That looks like an e. Sorry. C times cosine of wt plus gamma, and I factor out the minus, so that should become plus now, plus w sine t plus gamma. Okay.
That symbol, Professor, I'm sorry, I was mistaken. It's actually delta.
Delta! I was like, wait, doesn't delta. Okay, yes. I don't know why I'm having such a brain fart with that. But at any rate, okay. How's it looking? Is that okay? Questions on any of this? So this would be our first derivative. Let's go here. So this is equal to s of t. And s of t, the first derivative of a position function, is equal to v of t, the velocity v of t is equal to this. Good. So now that we have,
I think I did something like that. I was close.
Okay.
It just didn't feel right.
well, as I remember going through these as a student, in algebra, you just tend to be coddled a little that the problems are pretty easy, and so if you start doing something really wrong, you're like, oh, If the problem gets too complicated, it usually means you're doing something wrong. But unfortunately, in calculus, that's not always the case. It sometimes is the case that if you're working and it's starting to get really nasty, they're like, wait a minute, maybe I did something wrong. But unfortunately, sometimes the answers really are that ugly. So you're headed in the right direction here. And the second derivative is going to be even uglier, since now we have, well, okay, so we can redistribute this again. I would prefer to do the next derivative. I would prefer to think of it as distributing this again, and then I have two pieces that I need to find the derivative of, and each one of those pieces is going to have a product rule. So it's going to be exactly twice as long and nasty as the first derivative. Did that make sense? What I said?
Repeat that. I'm sorry, my grandson. Stop.
Okay, so we're gonna take the next derivative, right? I need to find the derivative with respect to t.
Right?
What's that?
The second derivative is acceleration, right?
Correct. The next derivative is going to be acceleration, right?
Okay.
So let me write that down. If we have s of t is equal to position, then the first derivative with respect to t of s of t, which we also denote as s prime of t, is equal to velocity. And now if we take the derivative with respect to t of the velocity function, velocity, which is also d dt of s prime of t, oops, I don't know what just happened there. Oh, that's not good. Okay, so then that is also known as s double prime, right? The second derivative of the position function, which is the first derivative of the velocity function. So at any rate, we just have to go back to this thing and take the derivative one more time, and that'll give us the acceleration function. Good. Okay, so to find that, when we do that, I would rather go back and redistribute this. So I'll end up with s of t is equal to negative a e to the negative ct times another c. So maybe put a c out here and put a minus there. Cosine of negative t plus delta plus w. Oops. I need a minus a. Minus a w e to the negative ct sine of wt plus delta. There. So all I did was distribute this to each of these. And now when I find the derivative with respect to t, I'll have this as one thing I have to find, and this as another thing I have to find. I might even do them separately. And within each one of these, there's going to be a product rule. Right? I have a product rule here, and I have a product rule over here. So it's very similar to what we just did. We just have to do it again, twice, and then bring it all together. Why is this zooming in and out on its own? It's really not fun. Okay, anyway, so that's a good place to stop with this one. And I think I better move on to Chapter 5 review now. So try the other ones, and if you need help, let me know. Okay, so Chapter 5 review on integrals. I just briefly went through the chapter just to kind of look at the various concepts that that you guys went through back in your Calculus 1 class, and just kind of spotted all the main concepts, basically anything with a giant box in it. And I just thought we'd go through it real quickly and then maybe look at some of the review questions at the end of Chapter 5. This is not to say that we're going to, relearn everything from Chapter 5. So I'm quickly going through a lot of this stuff. Hopefully it's very familiar, and if not, then you can go back to Chapter 5 or your notes from Calculus 1 to make sure that that you understand these ideas. Okay, so let's get started then. Chapter 5 introduces the idea of finding the area underneath a curvature. So a classic example is something like this. We have the function y equals to x squared. Here it is. And then we could be interested in finding the area underneath the curvature, right? The concept that we develop is to approximate it, right? We kind of give up on finding the exact answer. So the first thing we do is think, well, let's come up with a good approximation. And that approximation can be created. One way to do that is to come up with rectangles, right? So we come up with rectangle approximations. So here is a nice little image, a nice little picture where we have 1, 2, 3, 4, 5, 6, 7 rectangles. 7 rectangles being used to approximate the area underneath the curvature. So we can see from the picture that it does a fairly good job, but there are little corners here where it's not going to be exact. Good. Here's another example, right? And the difference between these two is where we choose the height of the rectangle. Here we're using all the left endpoints, right? Each rectangle goes up to a height where the left corner of that rectangle is what touches the function at every one of these points, the left corner. Whereas in this example, this is a case where they're all right corners. The right corner of each rectangle touches the function. So in this case, we are slightly underestimating the area, right? Because there's a lot of white gaps there, right? All the rectangles are a little bit below the function. So we're underestimating this area by a little bit. Whereas here, we're overestimating it, right? At every point, the rectangle ends up going above it by a little bit, right? So we're doing a little bit of an overestimation. And then, of course, if we want to get an even better estimation, what do? We do more rectangles, right? So here are some images of 10 rectangles, n equals to 10, 10 rectangles approximating that area. Here's 30 rectangles, here's 50 rectangles, all approximating them. And in all 3 of these cases up here, we have overestimations. We have right endpoints on each rectangle. Whereas in these 3, they're all being underestimated. Left endpoints on the rectangles. Good. There's also some really nice apps out there that do the exact same thing. So I pulled up a couple before. So if you just Google Riemann sum area under a curve, there's a lot of them out there. So here's just one quick one. So here again, we're trying to find the area, this area right there underneath the curvature. And I could see that the actual area is 9. The answer should be 9. Okay? So what we could do is we can approximate it, and we can begin by approximating it with 3 rectangles where I'm using the left endpoint. So here is one rectangle where the left edge, the left endpoint of the rectangle is what touches the function, right? Meaning that I'm evaluating the function at x equals to 2 to get to this height right there, and that establishes this blue rectangle's height. Good. There's the second rectangle, and I'm using the left endpoint, which means that 1. I'm evaluating my function at 1 to get this point. That's how I get this rectangle. And then the third rectangle is actually this one down here, where the left endpoint is the value 0, so it's got a height of 0. So height of 0, and then this rectangle, and then this rectangle. So there's 3 of them. And that's my approximation. At the moment, that approximation, the area of the 2 blue ones adds up to 5, which is not a great approximation to that 9. But as we increase the number of rectangles, right, from 3 up to 5, now I have 1, 2, 3, 4, and then that 5th one is still that 0. Now that area is 6.48, getting closer to the 9. Right? And as I make more rectangles and more rectangles and more rectangles and more rectangles, right? The more rectangles I have, the closer my approximation is. the sum of all those blue rectangles gets closer and closer to being the area, the exact area of that green. So we know that the exact area is a 9, and at the moment, with 37 rectangles, I'm getting an 8.638, right? So I'm getting closer and closer and closer. And the more I have, the more I have, the more I have, the closer and closer I get to the answer, right? If I ever stop, I'm never going to have the exact answer. If I stop at 100 rectangles, if I stop at 1,000 rectangles, if I stop at 100,000 rectangles, not going to be the exact answer. However, we know that as we let this go to infinity, as we have an infinite number of rectangles, at infinity, it will be exactly equal to 9. Okay. All right, well, let's get back to something more like this. Another thing we could do is think about the location. So here we're doing left end, very popular, but we can also do right end. So now I'm letting the far right edge of the rectangle determine the height of it. Right? So here is the little subdomain that determines this final rectangle from there to there. So if I use the far right edge, I'm letting this x equals to 3 determine the height of that rectangle. And then in this rectangle, if I'm using the far right edge, I'm letting this value, whatever it is, to determine the height of the rectangle. Right? So here's an example where I'm using all right edges. At the moment, I'm overestimating it by a little bit. It's saying that the sum of all those blue rectangles is 11.88, when I know the answer should be 9. But as we let n go to infinity, more and more and more and more, we get a closer and closer and closer approximation. So at n equals to 30, I already have a pretty good approximation. I'm overestimating it for sure, but you know, it's a pretty good guess. So right now the area of all those rectangles is 9.455, when I know the answer should be 9. Right? So then we keep pushing, keep pushing, keep pushing, and when we get to about 80, look, we have a very good approximation. Good, 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 good. Okay, let's get back to something closer to here. Okay, so the right endpoints, very popular selection. The left endpoints, very popular selection. Another popular selection is to go right in the middle, the midpoints. Right? So here in each rectangle, what we want to do is find the middle value of the x, in the x-axis, the middle value in that little rectangle, and then use it to determine the height. The advantage of this is that you get a better approximation, because sometimes your rectangle is going to be a little bit higher than the function, as it is right here, but then sometimes it's going to be a little bit under. So this little green part that we're not counting, that we failed to count by our rectangle, is kind of balancing out with this little blue part here that we're using to overestimate. Right? So we're overestimating this little chunk, we're underestimating this little chunk. Those two kind of balance themselves out, and we get a better approximation. Right? Look, with only 5 rectangles, I'm already very close to the answer. Right? The sum of all 5 of these blue rectangles is 8.91, which is very close to this 9. Good. Okay, so then as I increase this to more and more and more and more rectangles, I get closer and closer and closer and closer and closer to the real answer. So look, after 80 rectangles, the sum of all those blue rectangles is 8.99965, really close to the 9. Not exactly the exact answer, but very close. Right? Whenever we stop at any integer value, any actual value of n, no matter how big it is, we're never going to get the exact answer. It's always going to be a bunch of 9s here, really, really, really close to it. Or maybe just a little bit above it, 9.00001. At the end there might be some constant. It's never the exact number unless we let n go to infinity. At infinity, when we let it go to infinity, it equals to exactly the area under the curve, which is 9, in this example. Any questions about any of this? Okay, so if you want to play with one of those, you can Google one of those guys. Okay, so that was the idea first introduced in Chapter 5. And then here is the sort of math description of all of that. We want to introduce this. This is when they first introduced this notation of an integral symbol, right? This integral sign from a to b to represent the area underneath the function, right? And then it's equal to this Riemann sum, right? This is a sum of rectangles, where the base of each rectangle is this delta x, and then the height of the rectangle is this, the function evaluated at some point x sub I star, where each x sub I star is a value inside the domain of each rectangle, right? So you can find the height of each rectangle. And then you let n go to infinity to find an infinite number of rectangles, and we sum them all up, and then that is equivalent to the area underneath the curvature. Right? So let's read this. If f is a function defined for x being between a and b inclusive, we divide the interval from a to b into n subintervals of equal width, where each rectangle, each width, has a base of b minus a divided by n. That's where that delta x is. So in this initial description of the area underneath the curvature, we stick to cases where we have rectangles of equal width, but that's not always the case. It's not always required. You'll see some point down the line. But for now, let's just kind of visually see what that's saying. So if we have x, the function defined on some interval from a to b, right, inclusive of the endpoints, so the function is defined there. So let's say the function does this. Here's f of x. Okay, so it's defined there, and it's defined here. Good. Okay, so now we're going to take that area and we're going to divide it into subintervals. So there's these little subintervals that come like this, dot, 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 and then there's some intervals over there. And they're all of equal width. So the width of each rectangle is going to be delta x, right, which is equal to b minus a over n. And that'll give you the width of each one of these. That one's a delta x, this one's a delta x, this one's a delta x, right, all the way out to the end. This last one is a width of delta x. Good. Now for each rectangle, we need a width, right? That's what this is. But we also need a height. So how far up do we go? Should we use this point? Should we use that point, right? So for this arbitrary kind of selection here, and we go up, where should we stop? Should we go all the way up to there and go like that, where we use this point there, right? That could be one choice. Or should we go on this edge and go up to there and kind of go like that? That could be another choice for our rectangle, right? So where do we go? How do we figure that out? Okay, so that's what these little stars are. X sub 1 star, X sub 2 star. This is saying that for every rectangle, choose a value in there. And it doesn't really matter where that value is. It just has to be inside that rectangle. So X sub 1 star is going to be somewhere in here. It could be the left point, it could be the middle point, it could be the right point, it could be anywhere in there. It's just some point in there. And then X sub 2 star is going to be some point here in this little section. It's got to be in the domain, in the footprint of where that second rectangle is going to be. And somewhere in here will be the third one, X sub 3 star, will be some value in the footprint of the third one, right? So very common ones are the left endpoint, the right point, or the middle point. But in calculus, and based on this definition, it actually doesn't really matter where it is. And as long as we follow this process and let it go out to infinity, when we have an infinite number of rectangles, it doesn't matter where you choose your stars to be. It doesn't even have to be a uniform decision, meaning that maybe x sub 1 star is the left endpoint, maybe x sub 2 star is the middle point, maybe x sub 3 star is the right endpoint, right? It doesn't matter as long as it's something in there, right? X sub 1 star is a point in the footprint of the first rectangle. X sub 2 star is something in the footprint of the second rectangle, and so on and so forth, right? So thinking out to the nth rectangle, some ith rectangle in the middle of all of this, right? There's some ith rectangle. We know its width is still going to be delta x. But then we choose some random point, just kind of randomly picking it. Let's say it's that one. That would be the ith x sub star value somewhere in there, which means that I go up, and then that will determine the height of the rectangle, right? So this right there, that point would be the ordered pair x sub I star, comma, f of x sub I star. Right? And then that would be the height of this thing. I go this way, I go like that, and there is my ith rectangle. Good. It's got a width of delta x. Delta x is a fixed formula, b minus a over n. But the height varies. Now, when I'm only doing a limited number of rectangles, the sum of all those rectangles will vary based on my exact choice of the x sub stars, right? That list. Midpoints will be different from left points, different from right points, but as we let them go out to infinity, the number of rectangles go out to infinity, they will all equal the same thing. Okay, so that's everything that this is trying to tell us. This was an introduction to area underneath the curve as the Riemann sum, and then letting the Riemann sum go to infinity. Okay, so reading the whole thing. If f is a function defined for a less than or equal to x less than or equal to b, we divide the interval from a to b inclusive into n subintervals of equal width, delta x, which is equal to b minus a over n, and let x sub naught equal to a, x sub 1, x sub 2, and x sub n equal to b. Okay, so don't confuse them with the stars. X sub naught refers to the fact that it's this guy. X sub naught is equal to a. Good. And then x sub n is this last guy over here. X sub n is equal to b. Good. And then we're really looking at the edges of each rectangle. So now this guy right there, that edge right there would be x sub 1. And then this edge would be x sub 2. This guy here would be x sub 2. Good. And remember that because the widths are always delta x, it's true that x sub 1 is equal to a, wherever a is, plus 1 copy of delta x. Good. And x sub 2 is going to be equal to a plus 2 copies of delta x. And so on and so forth, until eventually you get to the end. Good. Okay, the endpoints of the subintervals, and now we let x sub 1 star, x sub 2 star, all the way out to x sub n star, be any sample of points, right? Any sample points in the subintervals, so that the x sub ith star lies in the ith subinterval, which is going to be described by these endpoints. So based on our description of everything, it's going to mean that this guy is going to have endpoints of x sub I, and this one is going to be x sub I minus 1. Right? It's pretty heavy on the notation, I know, but hopefully this is review. And also keep in mind that you can always go back to chapter 5 or your notes from calculus 1 if you need to to be reminded a little bit. Okay, then we define the integral of f from a to b, right? We introduced this notation, the integral from a to b of f of x d of x, to be equal to this guy, the limit as n goes to infinity of this Riemann sum. Provided this limit exists and gives the same value for all possible choices of the sample points, if it does exist, we say that f is integrable on a to b. Whew. So there's a lot there, right? It's just one cute little box, but I'm sure that when you first saw this the first time, it probably took days and days and days to really carve it out and really think about what that means. Okay. All right. Moving on then. So like I said, I just picked out some of the most important things from chapter 5, an introduction to integrals. So moving on. So if f is continuous on a to b, or if f has only a finite number of jump discontinuities, then f is integrable on a to b, including the endpoints. That is, that the definite integral from a to b of f of x dx exists. Good. So finite number of jump discontinuities. Remember what a jump discontinuity looks like. So if we have our function, here's our x-axis, here's our y-axis. So if we have our function do this, like say it does that and it jumps to here, like this. And we want to integrate from a to b, from a to b. This is guaranteeing that we have that we do have an answer, right? The area underneath the curvature does have a solution. A jump discontinuity can also look like this, where we just have like a little hole that pops up. So let's say we have this, and then at that little hole was actually this up here. And maybe we have another one. Maybe this one goes like that, and at this little hole, the function actually goes down here. Okay, so this is saying as long as we have a finite number of them, as long as we don't go crazy and go out to an infinite number of little jump discontinuities, then everything should be fine, right? So if the function is continuous almost everywhere except for a finite number of jump discontinuities, then f is integrable on a to b, and so this integral will exist. Okay, so that's just a nice little thing to know. This is okay. So up here we gave a more general description, and we allowed the x sub I star, x sub 1 star, x sub 2 stars. We allowed this to be any sample of points on the subintervals. But you know, like I said, left endpoints and right endpoints are very popular. So this is just a restatement of the same thing, except we're allowing the values for this guy to be equal to the left endpoints, I believe. When, let's see, when x equals to 1, right? Sort of, if we follow the instructions here, as I goes from 1, then the limit as n goes to infinity will have f of x sub 1 delta x plus f of x sub 2 delta x plus dot 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 dot. Okay, so x sub 1 is equal to a plus 1 times delta x, right? So this is going to be a right endpoint. The very first rectangle is being evaluated on the right edge, right? On the footprint of that first rectangle, we want to go to a plus delta x, which is going to put us on the right endpoint. Does that make sense? We have a function that does this, and we go from a, and I'm just going to kind of exaggerate this a little bit and go way out here, like that. Then this is going to be our first rectangle. We're going to let x sub 1 be equal to a plus delta x. Remember that the widths of each one of these rectangles is going to be delta x. So this is going to be x sub 1. X sub 1. It's a plus delta x gets you here. So this is going to describe right endpoints for my rectangles. Right, where I'm using this to judge it. And then x sub 2 will be this guy. Remember, x sub 2 x sub 2 is equal to a plus twice delta x, just following this little formula. There's a little sub 2 there, therefore there should be a 2 there. And a with plus 2 multiples of delta x lands you there. Right, so the second rectangle is going to use this as its height, right there. And then that would be the next one. Good, so I begin my approximation that way. Good, good, good. So this is just almost a restatement of this one, except this one's more general, that allows you to choose any subinterval. I'm sorry, not any sample, any sample points, as long as they satisfy the condition that each sample point comes from the little footprint of each rectangle. Whereas this is a way of describing the right endpoints. Right endpoints. Of each rectangle. Good. Questions, 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 questions. Okay, some more properties of integrals. The integral from b to a of f of x dx is equivalent to negative times the integral from a to b of f of x dx. So this is just pointing out that we're allowed to exchange these, right? This goes from a to b, and this one goes from b to a. Right? So this is saying that the arithmetic of how we figure this out, it's going to give us an opposite sign if we interchange these things. So we have to introduce a -1 in order to get that they both equal each other. Right? So again, just to give you an image to hang on to, again, if we have some simple function, say we have that, and it goes from a to b in this order, then the area underneath the curvature is this, right? Just a rough image to hold on to. Y-axis, x-axis. Okay. So based on the way I drew it, it should be clear that this area should be positive, right? So the integral from a to b of f of x dx, just based the way I drew it, this should be this area in red, and it should be positive. And this is letting me know that if in fact I switch around the limits of integration and I switch it from b to a of f of x dx, the fact that I switch these limits here is going to result in a negative number here. So we have to introduce another negative in order to make them match, so that we can keep that equality. Okay. Moral of the story, we can change the limits of integration as long as we introduce an extra minus. Okay, another property of integrals, that if we're integrating from a to a of this function, the answer is 0, right? Again, sticking to this generic description of area underneath the curvature, I have my function, and I want to integrate starting at a and ending at a. So really, I would just be integrating a little sliver, right? An infinitely thin sliver, which has an area of 0, right? If I squeeze this b all the way up to a, there would be no more red, right? Good, that's what this is letting me know. Okay, some good properties of integrals. So if we're integrating from a to b on a constant c dx, right? So pay attention to the dx. People often kind of overlook that. This little dx is letting me know what the variable of integration is. The variable of interest here, the variable integration is an x. So a c in this case represents a constant, even if they didn't highlight it over here to let me know that it's a c. Because it's a constant, then the integral from a to b of this constant equals to a rectangle which has a base from b minus a up to a height of c. Again, just to give you a little picture of what to kind of look at. Man, these things are... Why is this... Okay. Just to kind of give you a little something to hold on to, if we have the x-axis, the y-axis, and we have some function y equals to a constant. Remember that whenever we have a function where we have a constant, then we have a horizontal line at c, right? This would be at point 0, comma c. Okay. Constant c. So if we're integrating from a to b, then the area underneath that curvature ends up being a rectangle. A rectangle that has a height of c and a base of b minus a. And if we multiply those two together, we get the area of this rectangle part, and that's what this is letting us know. Right? The integral from a to b on the function c, where c is some constant, dx is equal to c times b minus a. Okay. Questions, 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 questions? Okay, the integral from a to b of the summation of two functions, f of x plus g of x d of x, is equal to, well, we can integrate one and then integrate the other and then add them together. Right? The integral of a summation is equal to the summation of the integrals. Good. Keeping in mind that we keep the same limits of integration in both cases, and that's assuming that the f of x function is integrable, the g of x function is integrable, that this has an answer, therefore this will have an answer, and it will be equivalent to the summation of these two integrals. Good. Okay, so if we have a plus there, we can break it up into separate pieces. We use that a lot. And this fourth one, kind of skipping 3 for a second, is the exact same thing, except here we have addition, here we have subtraction. The integral of a difference is equal to the difference of the integrals. Okay. The integral of the difference of functions, is equal to the difference of these two integrals, assuming they exist, of course. And then number 3 was saying that if we have a constant in there, we can kind of move that constant outside this integral, and we can find the answer, then multiply that answer times the constant. We'll get the same result. Right? So we can factor out a constant. That's what that's letting us know. Again, just kind of flying through some of these ideas. If we have the integral from a to b of f of x dx, again, assuming that exists, this is going to be equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx, where c is some value in the domain of the function f of x, and usually it's somewhere in the middle, though it doesn't actually have to be. But just to give you, again, just a picture of what's happening. We have x, we have y, we have some function, here's f of x. And so we want to find the area from a to b. Right? So we have this area right here, area underneath the function, goes up to there, like that. Okay, so we want that area right there. Well, if there's some value c in the domain, and again, it doesn't have to be, but it usually is somewhere between a and b, and it's a nice way to visualize it. Oops. It's a nice way to visualize it, but I think there's some work out there. At some point you'll run into a question where they ask you to show that it works even if it's not in the middle. But anyway, so we can break up that integral and say, okay, let's find the area from from A to C, and then that gives you this green rectangle, and then we find the area from C to B, and kind of find this blue rectangle, and the area of the green rectangle plus the area of the blue rectangle must be equal to the area of the red, or not rectangle, sorry, the area of the green region plus the area of the blue region must be equal to the area of the red region, right? So the integral from A to C of f of x dx, that's going to be the green part, the green one, and then the integral from C to B, that's going to be this blue part, must be equal to, when we add those two areas of those two regions, they must be equal to the area in red. Not read, red. In red, from A to B. Good. Good. Okay, comparison properties of integrals. So if f of x is positive and x is defined between a and b inclusive, then the integral of f of x dx must be positive. Good. So the area underneath the curvature is positive whenever the function is positive and x is defined within a subintegral of the domain of the function f of x. Good. That should be pretty obvious. If f of x is always greater than g of x on this little subdomain, as x is ranges between a and b inclusive, then it must be true that the integral from a to b of f of x must also be larger, greater than or equal to the integral from a to b of g of x d of x. Good. I think that one's pretty self-describing as well, pretty intuitive. X, we have y. So if we have some function like this, and this is f of x, right? And then f of x is always greater than or equal to g of x. So let's do a g of x. So g of x is always less than or equal to it. So let's say that it touches there, but then comes back down, and then it touches there, but then it comes back down. So here is g of x. Right? And remember, we're not allowed to have sharp corners, so let's make that a nice smooth transition. Oh man, that's going to be ugly. Okay, so it comes up, maybe barely touches, comes up, maybe barely touches, and comes this way. But g of x is always less than or equal to f of x. It's only equal to it at a couple of dots, but it's almost always less than it on some domain from A to B. Right? Outside that domain, all bets are off. Right? So maybe way over here, this thing shoots up that way, and this thing shoots up this way. Who knows? But we're only interested in this little segment. Good. So as long as f of x is greater than or equal to g of x on this little segment from A to B, then it must be true that the integral from a to b of f of x is greater than or equal to the integral from a to b of g of x d of x. Okay. So the area underneath the curvature of the green one is always going to be greater than or equal to the area underneath the curvature of the blue one. Right? Because we just said that it's always true. Good. Now I drew it with both functions always being positive in that little segment, but that doesn't always have to be the case either, so something to think about. Good, but I think it's a pretty straightforward little property of integrals. Okay, so if f of x is trapped between lowercase m and capital M, right? So on some interval from a to b. So lowercase m is the smallest point of the function in that subinterval, and capital M is the largest value experienced on the function in that interval. Then it must be true that the area underneath the curvature is somewhere between these two rectangles. Right, so here's a nice little picture for it. We have ourselves our function, right? Oops, our function f of x is this one. Here's f of x. Oh man, that's really ugly. Do a better job, hopefully. So this guy is f of x. That. So this guy is f of x. The area underneath f of x is going to be all of this. This is the whole area of f of x. Okay, but now we're going to find the maximum point experienced within this little section between a and b, and that's this guy. This is the biggest one. Good. And then this is the biggest one. I'm sorry, the smallest one. Good. Good. Okay. So if we want to get a sort of an estimate of the area in red, that's what this is, area in red, right? That's this integral from a to b of f of x. That's all of this red thing, all of it. Well, this red thing can be approximated and have a low ball estimate, right? The smallest low ball estimate, and it can have a large estimate. The large estimate takes the largest value that the function ever took on, which is this point. So we could say, well, okay, one overestimation could be to think about this giant green rectangle where the base is from a to b, okay, a to b, and its height is this. This giant height here is capital M. So an overestimation is this giant green rectangle. Good. And an underestimation, the smallest possible underestimation, would come from thinking about a rectangle formed again by a base of b minus a, but then its height ends up being the smallest possible value that we know f of x took on. So it's this darker, darker blue. Let me make it even darker. This darker blue rectangle down here, which has a height there, which is the smallest value that f of x takes place. This is an underestimation in blue here. Any questions about that?
So like anything that's below the little m, it's the underestimation.
Right, so this becomes the little m times b minus a becomes the underestimation. That's why we know that the actual area in red is greater than or equal to that, right? If you knew, if you knew very little of this function, all you knew is that this is one dot and that it's the smallest this function ever becomes, then your smallest guess would be this one. Good. For example, let me give you like an example of where you would do this kind of thing. Let's say that somebody gets paid commission-based, okay? And their commission varies throughout the year. Sometimes they get a check that's this big. Sometimes they get a check that big, this big, that big, this big, right? So it kind of varies like this. Lots of checks. So maybe they're, I don't know, every week. So this week they got this much, this week they got that much, that week they got that much. Okay, so we kind of have a sense of the whole thing. So this would be the makings of my function that describes how much money they make per week. Okay, but people tend to kind of hide what they make, so maybe they're not very clear on that. But maybe you only have one value. You found one check one time, and this is the only check you found out about. Okay? If you also happen to know that this is the smallest, the smallest check, then what you could do is estimate it, estimate what the other checks are, because, all right, well, if you know this is the smallest, then you know the next one has to be bigger than that one, and the next one has to be bigger than that one, and the next one has to be bigger than that one, right? So you can kind of estimate them all to be this, and this would be your underestimation. Good. So then if you know, when it comes time to figure out, okay, well then how much money did they make for the whole year, and it comes time to add these all up, you can come up with this little rectangle down here, which would describe an underestimation based on the fact that you know this is the smallest one, right? Or we can likewise come up with an overestimation, where the overestimation is based on one single value, say this one, and you happen to know that this is the largest. Right? You only know one check, you know, one time you saw a check, and you also happen to know that it's the largest check ever received. So then you can assume that all the other checks are equal to or smaller, and come up with an overestimation. And so you can come up with this giant blue rectangle. Good. Just to put some numbers on here, let's just come up with, say that this is $1,000. $1,000 is the most he ever got, and the smallest he ever got was, I don't know, $100. Good. And then this is 52 checks a year, right? 52 weeks a year. So based on that, an overestimation would be that for the whole year you made $52,000. I only have 1 week's check. I know it's the largest one. I know it's $1,000. So my best guess for the whole year is, man, this person is making $52,000 a year. Good. On the other hand, if I know the smallest check was 100, I guess all the other checks must be equal to or higher. Then an underestimation would be that they make $5,200 a year. That's a pretty big difference, right? 5,200. So now I can say that the actual answer is somewhere between the two. Sometimes it's going to be a little higher than this, higher than or equal to this. Sometimes it's smaller than or equal to that. So it's somewhere in between the two. Good, good, good. Okay, so again, there's some nice examples in your book about this. So you know, you can go look at those up. I'm going to move on to the fundamental theorem of calculus. And as the title suggests, very important to calculus. It's in fact fundamental. Fundamental to calculus. And it's kind of a weird little description, right? So we begin by defining a function f, which is continuous on a to b. And then we move on to define a new function, g of x, which is equal to the integral from a to x, where a is some constant, of f of t dt. Good. Okay. And so now the first part of the fundamental theorem of calculus tells us that g of x is continuous on a to b and differentiable on a to b. Notice that this is inclusive of the endpoints, so it's continuous on a to b inclusive of the endpoints, and differentiable on a to b not including the endpoints. And this is the kicker, that the derivative of this function, g prime of x, is equal to f of x, the function that you're integrating. Good? I know. Mind-blowing. Okay. And then, just as you're, chewing on that, there's a second part to the fundamental calculus, which is really the most functional part of it. So if f is continuous on a to b, then the integral from a to b of f of x dx is equal to capital F evaluated at b minus capital F evaluated at a. Right? So this a and b are associated to the limits of integration. Good. And this is where the relationship between capital F and lowercase f is described this way. The derivative of the capital F of x function is equal to the lowercase f of x function. Good. Right. I have a nice little applet that kind of demonstrates what that means, because I know it can get easy to get lost in that. So let's see. So we already did this one. Let's work with this one. Okay, so let's say we have this function, x to the third power plus 1/2 x plus 2.25. Okay, so the antiderivative of this function is equal to this, and I know that we're still building that up, and we're going to get to these rules in a little bit, but right now I just want to do the graph, so hopefully this looks familiar. So by the antiderivative, I mean that this is a function such that when I take the derivative of this function, it equals to this one. Right? So think about this function right here. How do I take derivatives? We bring down the 4. It cancels with the 1/4. Subtract 1. That's how we get x cubed. Right? For this part, we bring down the 2. We get 1/2 x to the first power. That's how we get that guy. 2.25x. So we bring down the 1 from the exponent, and then we get the constant, 2.25. plus some constant c. Okay, so this is the antiderivative of this function, or we could say that given this function, this one's the derivative, or given this function, this one's the antiderivative. Good, good, good. Okay, so this red one is the function f of x. So now if we define a new function which is equal to the integral from a to b of this red one, we end up with this. Right? We want the area underneath the curvature. So I have a little slider here that indicates the a value, and then we have a little slider here that indicates the b value. Right? So here is the area underneath the curvature from a to b. Good. So here's a little integral sign, the integral from a to b, where right now the a is a negative 0.5 and the b is a 0.7. So the integral from negative 0.5 to 1.7 of my function f of x, lowercase f, that would be this one, dx at the moment is equal to 7.6824. So the computer is automatically calculating it as I move it. So at that point, it's equal to 2.804 and so on and so forth. Okay, so we have a description. Oops, we have an hopefully a pretty good idea of the area underneath the curvature in terms of this integral. Good, good, good. Okay, now the antiderivative function. If I graph the antiderivative function, I get that. Right, that's this green one. And now if I change the constant value c, it'll shift the function up and down. Right? So when we find an antiderivative, we know we always have to think about plus c, plus a constant, right? Because when I take the derivative of a constant, I get 0. So I can make this a plus 8, a minus 2, any constant, and it doesn't change the relationship between these two. But in terms of the graph, it does change it a little because it'll shift it up and down, right, based on the constant. So let's leave it at a constant of 6. There it is. Okay? All right, so part 2 of the fundamental theorem of calculus indicated that if I go to the antiderivative function, capital F of x, and I find, if I evaluate it at the endpoints and subtract them this way, I'll get the same answer. Right, so here is the antiderivative function f evaluated at a, that's this guy, and then b, that would be this guy, and if I subtract them in that order, I get 3.01, which is the exact same answer that I got over here by using the integrals, right, by solving it with the integrals. Right? And that stays true no matter where it is. So if I move this b value, I still get the same thing. Right? Either way, I get the same answer. Any questions about this? Right? So this is helping visually reaffirm that this is true, right? The actual area in purple, which is the integral from a to b of f of x dx, is in fact equal to finding the antiderivative of f of x and then evaluating at the endpoints and subtracting it in this order, right? Where the relationship between these two is that the derivative of this function equals this function. Any questions at all? No? 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 And again, notice that the constant can be anything, so this green one can be shifted up, could be shifted down, right? Could be shifted up and down, but the gap stays the same. The answer stays the same. This area in purple, I can find it by integrating this function. The calculator already did it for me and found a 2.74. Or I can find the antiderivative of f of x, evaluate it at two endpoints, subtract them in this order, f of b minus f of a, and I get the same answer. Any questions before I move on? No? All right. Let's look at one other one. Same thing. We have some function f of x equal to sine of x plus 1/2 x. That's this function right here. Okay. So if I want to find the area underneath the curvature from a to b, it would look like this. Right? Here's the area underneath the curvature from a to b. And right in here, you could see that the computer's already calculating it for me. Right? So I could do the limit definition. I can start thinking about rectangles here, and then finding the area of each rectangle, and then adding them, and then letting it go to an infinite number of rectangles, doing it that way. That's one way to find the answer to this purple one. Okay? But an easier way to find it would be to come back to our function f of x, here it is, and think of an antiderivative, something whose derivative equals f of x. Right? So remembering that the derivative of cosine is negative sine, then that means that the derivative of negative cosine x equals positive cosine x. And the derivative of this, right, we bring down the 2. 0.25 times 2 is 0.5, x to the power of 1. And the derivative of a constant is 0, which means it disappears. So here is my antiderivative function. So if I graph that, it looks like this green thing. Good. Now let me bring back this guy, because otherwise it's going to be off charts. Okay, let's go like right there. Okay, so if I wanted to find this area in purple, then one way I could do it is think about the antiderivative and then evaluate my antiderivative as capital F of B minus capital F of A, right? Doing that. Here's A, evaluating F of A is there. Here's B, evaluating F of B is right there, right? Here is F of A, here is F of B, capital F of A, capital F of B. And if I subtract them, I get f of b minus f of a equals to 14.998719, which is the same answer as this one. Good? Questions? Questions? And as I change the integral, you see that it continues to work. Right? The area here in this little purple is 3.0173, that. And now f of a is this value, capital F of a. Capital F of b is this value. And if I subtract them in this order, I get the same number, 3.01734227, that guy. Good. So further reaffirmation that that property is true. And again, pointing out that this constant at the end here won't matter. If I shift that up and down, I still get the same answer. The 3.017, that doesn't change. Stays the same no matter where I put it. way down there. Right? I can make a negative 6.6 constant that brings that antiderivative function way down here, and the gap stays the same. So this is still the same answer as that. Okay. The only thing that matters is this, the limits of integration. Okay. No matter what I do, the area in the purple is equal to the difference between these two values. Okay, so we should be totally satisfied that this is true. The integral from a to b of f of x dx is equal to capital B, capital F of b minus capital F of a, subtracted in this order, right? Paying attention to the limits of integration here, as long as the relationship between these two functions is described as this. The derivative of capital F equals to the function f of x. Good, good, good. Any questions on that then? So this is part 1 and part 2. And then your book goes through a bunch of examples and a lot of explanations and some proofs. This is a great proof to go through and hopefully, try and understand it. I think that maybe at this level in your math career, it probably is unfair to demand that you know how to do it and can, kind of repeat it on a test or something. So I wouldn't do that. Well, this isn't even Calculus 1, but in Calculus 1, I wouldn't have demanded that. I don't know if your teacher did when you did it, but I don't think it's fair at this point. But it is, I think, fair to say, try and go through it, try and understand it. First, you got to crawl before you walk and walk before you run. So at this point, if you can at least understand it, that way down the road, if you're sticking to math or in some of your engineering classes, there might be some proofs that you have to know. And if you're already kind of submerged in that field, it'll make it a little easier. Okay, so again, I'm just kind of picking out the main ideas in Chapter 5. And then they put them together like in kind of like wallet size here, fundamental properties 1 and 2, just kind of trimmed the fat and gave you just the main ideas. That's what that is. Little wallet size. Who doesn't want the fundamental theorem in wallet size? Okay, some more properties of integrals. So the integral of f of x dx equals to f of x, right? So notice that this is an indefinite integral. There's no limits of integration, right? Means that the derivative of the capital function f of x equals to f of x. So it's the exact same things we've been saying. Then the book gave you a nice little table of useful integrals that are based on our derivatives, right? So if you remember derivatives from back in Chapter 3, then these integrals make sense, right? Since they're the antiderivative, right? Good. That's what this is establishing, right? The derivative of capital F of x equals lowercase f of x, meaning that capital F of x is the antiderivative of f of x. Good. Okay, so these are all really established or kind of translated over from our Chapter 3 study of derivatives. But we get to use these, no questions. Just use them, apply them. We've already kind of talked about this, so it's just, before it was presented as f of x dx, and then a little side thing that indicated for you, by the way, lowercase f of x, right? So the difference between this and the one right above is that we have from a to b of f of x dx, but then they noted, oh, by the way, capital F of x equals f of x, and all of this equals to f of b minus f of a. Well, it just makes it a little easier to rewrite it with a capital F prime of x here instead of f of x. That's all this is. It's just notation. Nothing really new, nothing new to see here. And finally, the last concept in Chapter 5 was this idea of the substitution rule. if u equals to g of x is a differentiable function whose range is in the interval I, and f is continuous on I, then it must be true that the integral of f evaluated at g of x times g prime of x dx is equal to f of u du. Ooh, that looks messy, right? But this is the idea that allows us to have the u substitution properties, right? And it's kind of messy, so I'm just going to rewrite it in a sort of larger way so that it's clear. So we have f of, and then we're evaluating at g of x times, and then we're going to have this g prime of x dx, right? Remember that when we did u substitutions, we said let u equal to this g of x thing, right? This guy. Okay, so that part's going to be easy. It's going to be the integral of f of u, right? Because I'm just replacing this g of x with a u. Okay, but now I have to think about what this is, right? So what I do is I got to think about taking the derivative of this function u with respect to x. So d dx of the function u is equal to d dx of the g of x function. Well, d dx of the g of x function is in fact exactly this, right? It's this notation, same thing. And this is the same notation as this, du dx. Good. So now I can multiply both sides of the function by dx, and I can get my du is equal to g prime of x dx, which is this part. Good. So here we had u, and now we've shown that under that description, as long as u is defined as g of x, this is du. So I can rewrite it as the integral of f of u times du. Right? And that's what this is saying. Good. Questions, 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 questions. I know, very dense stuff here. We're flying through material that probably took a month to go through, and we're going to cover it in about an hour. Okay. All right. This is a nice, useful integral. The integral of tan x dx is equal to the natural log, absolute value secant x, plus a constant. Again, a useful identity to have, a useful property of integrals. And your book, I think, goes through a nice description, proof of why that's true. Some examples. So if that doesn't look familiar, look for it. And then moving on, we have just the last couple of concepts in that chapter. This is sticking to the substitution rule. It's just adding that it works in a very similar way, almost identical way when we have limits of integration. Right, so this is again my u substitution, letting u equal to g of x, and then taking its derivative will allow me to replace this part by du. However, now we have the limits of integration now change from a to b to now g of a and g of b, right? And that's because u is described as g of x. Good. Good, good, good. We're about to do some examples from that section. We're going to go through several examples, and we'll rely or come back and rely on a lot of this stuff. So I'm sure we'll do some u substitution cases where we see this being implemented. And again, if you don't remember at all, this is the end, like one of the last few concepts in chapter 5. Okay, and then the last useful idea in that chapter, finally, is this, that if f is continuous on an interval from negative a to a, and if f is an even function, right, remember the description of what an even function is, that means that f of negative x equals to f of x, then the integral from negative a to positive a of f of x dx is equal to twice the integral from 0 to a. Good. Good. If f of x is odd, and again a little description of what that means, then the integral from negative a to a of f of x dx is equal to 0. Let me give you a quick little visual of what all this means. It's for any even function, but a classic even function is just x squared is even. So if you think about that function, and just this guy goes that way, and this guy goes that way, right? And we have a y there and an x there, and we have values from negative a to positive a, like that. Good. So if we're trying to find the area underneath the curvature, oops, something like that. Let's make that the a. Whatever. It's ugly, but you get it. If you want to find the area underneath the curvature, because it's even, then what this is saying is the area underneath the curvature from negative a to a is equal to just finding the area from 0 to a and then doubling it, right? From 0 to a and then doubling it. The area in the green, if you double the area in the green, you're going to get the area of the whole red. Seems pretty obvious. Good. And then on the other hand, if we had an odd function, remember a classic odd one is just this, is odd. And if we had a nice, well, let's just use this line then. If we had a nice description like this, and we had the odd function, remember that this kind of looks like this. Very ugly, but you get the point. Okay, so if we go like here, this is negative a, and here this is a. So here is the area underneath the curvature trapped between the function and the x-axis. Here is this area over here, and remember that when we are dealing with these areas, when the area is below the x-axis, we consider it to be negative, right? This is negative because it's below the x-axis, and this is positive because it's above the x-axis. And because it's true that f of negative x equals to negative f of x for an odd function, then it's going to be true that this area is going to be almost the same as this one. They're going to be the same magnitude, the same quantity, but opposite signs. This one's going to be negative, this one's going to be positive. Therefore, the integral from negative a to a of f of x dx is going to be 0. Good. Questions? Okay, so yeah, that was a whole chapter in calculus in about an hour. Just all the highlights. I'm sure that there's probably 1 or 2 things in there you don't quite remember. Make sure you go back to your calculus notes and review some of that stuff. But let's move on to the end of that chapter where there's a bunch of examples to consider. And let's see if we can do those, or at least a few of those. So let's get rid of this stuff. Okay, so hopefully you've been doing the homework, and so I can kind of, I don't have rely on your direction. So I think I assigned the odd ones from 1 to 60 something. So let's start with the single digit ones. Are there any questions about anything in the single-digit ones? Let's do at least one of the single-digit ones. Like number 1, or number 3, or number 5, or number 7, number 9. Anybody?
I wasn't really doing that. I was on 7.1. Oh, that was my bad.
Oh, that's fine. You've moved on ahead, so there's no problems there. But
I have a question on 7.1, but it can wait.
you have a question on where?
7.1.
Oh, 7.1. Yeah, we're not there yet. So you can you can hold off on that. We're going to get to that, maybe even today, depending on how many questions there are from this review one. But does anybody have any question on questions from Chapter 5 review? Starting with the single ones, single digits, 1, 5, 1, 3, 5, 7, 9. Any questions?
I'll work on it tonight. Review.
Okay. So no questions? Here, let me pick one then if there's no questions. So number 1 is to do a Riemann sum of 6 intervals. So we talked about that. We got to come up with a nice approximation where we come up with 6 rectangles. And we want to integrate this region from 0 through 6 with 6 subintervals. So it makes sense. It makes sense that each rectangle is going to be exactly equal to one of these squares, right? The footprint of the rectangle is going to be one of these squares. Okay. Can we make sure to turn off our mics if we're not talking? Because all that background noise kind of gets in the way. Thanks. But please, unmute yourself if you have a question. Okay, so each one of these rectangles is going to have a base of 1, so that should be really easy, right? And then we want to think about left endpoints. So if we're going to use all left endpoints, then this one is going to have a rectangle there, right? Using this as a left endpoint, right? And then the next rectangle is going to use this as the endpoint, which is going to go up to there. So there is going to be my next rectangle. Good. Using left endpoints. Using left endpoints, my next rectangle is going to be there. So then I'll overestimate a little bit by coming out too far. Right, so we get an idea of what left endpoints means. Good. So evaluate our function at the left endpoints. In this case, it means we just kind of guesstimated, right? We're not going to get an exact answer since we don't have the equation of the function, but we have a pretty good guesstimation of what it would be. So just kind of guess what it is. There's not an exact answer to this, but you should be able to get something kind of close. Good, so do it once with all the left endpoints. It'll be 7 little rectangles that you have to multiply. All of them are going to have a base of b minus a over n, which in this case is all going to be 1. Right? They're all going to have a base of 1. Good. So no questions on number 1? Okay, moving on then. Number 3, evaluate this by interpreting in terms of areas. Oh, I love these kinds of questions. Okay, so how can we interpret this in terms of an area? So the function y equals to x is a straight line that goes through the origin. And so the integral from 0 to 1 of that function should be a triangle. Good. And the equation y equals to the square root of 1 minus x squared should be the top half of a circle, right, centered at the origin with radius 1. Good. And now if we're integrating it from 0 to 1, it should be a quarter of a circle. Good. So turn them into geometric shapes, and then it should be really easy. This would be a giant triangle. You can do 1/2 base times height to figure out the area of that triangle. And this one should be 1/4 of a circle. So multiply, use the area formula for circle, the formula for the area of a circle, and then multiply that by 1/4, and that should be the answer to this one. Good. Any questions on number 3? Number 5. This is going to be really easy. Find the area, the integral from 4 to 6 of f of x dx if we know that 0 to 6 of f of x dx is 10 and 0 to 4 of f of x dx is 7. Right? So remembering one of our properties, that the area of this one plus the area of this one must be equal to the area of this one, right? Since this one goes from 0 to 6. So 5 should be pretty easy, right? Okay. 7. The figure graphs f prime, the integral of 0 to x of f t dt. Identify each. Explain your choices. Okay. Did anybody figure this out already? Well, this one can only possibly be either B or C. What's that?
Yeah, I was gonna go with B as the original and C as the derivative. That's right. It's like B stops. Maybe
Okay.
that's wrong.
So let's see. That B is the original, and that C is the derivative. Therefore, A must be this one.
Yeah.
Okay.
Because B is going up, and
So,
then when it starts going
and C.
down, that's where A hits the 0 point at the derivative. I mean, C hits the 0.
Okay, hang on. So if B is the original, then we're looking at tangents of this function, right? The tangents. Over here, the tangents are positive, right? Tangents are positive. But C has negative values. So C can't be the derivative function of B. Okay, let's try something else. No, that's good. I mean, you got to try different things, kind of a guess and check. Try one thing, see if it works, try another one. Luckily, there's not too many combinations, but eventually you should get to something that hopefully makes sense. So let's try it the other way around. How about if we make that one C and that one B? So if this is the actual function, and I'm thinking of the derivatives, so the slopes of the tangent lines, they start off at 0. Oops. Yeah, C. So they start off at 0, and yeah, that's where B starts off at 0. And then I get slightly more positive, more positive, more positive, more positive, more positive, right? And that's what's happening here. The numbers are getting bigger and bigger and bigger and bigger and bigger. I reach a maximum there, meaning this is the steepest it gets, right around there somewhere. And then it becomes smaller positive, smaller positive, smaller positive, smaller positive, until I get back to 0, and that's what happens there. Then a small negative, bigger negative, right? And that's what's happening here. So that seems to make sense for these two. The original function is f, and its derivative function is b. Good. And now for the area, let's erase this over here. Let's make sure that it makes sense. I'm integrating c, so the area, if f is c, then I'm integrating c Yeah, okay. So it starts off at 0, and then as I'm integrating this, right, as I'm finding this area, I'm going into the negatives. And so A begins by going into the negatives, right? Negative, 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 negative. So from there to there, they're all negatives, right? This area here is some big negative value. It's the biggest negative value I'm going to get, and that's where we get this value there. As I start creeping into the positives, I kind of start canceling off some of that negative area. So it becomes smaller and smaller and smaller until we reach here, right? So this point here indicates the point where this area underneath the curvature and this area above the curvature both cancel each other out, and we get a total area of 0. That's where that guy is. Good. And then I keep adding more and more area. So then this comes all the way up to its maximum point. And then I begin to subtract area. A little bit of subtraction, a little bit of subtraction, a little bit of subtraction, until I get to that point. So this is indicating that this is again a 0. This indicates that this area, which is negative, and this area, which is negative, are equal to this area, which is positive. They both cancel out and give you that point right there. And then I continue to add a little bit more negative area, more negative area, more negative area, which means that this function continues to come down here, and that's where we end our whole thing. Good. So this is saying that this area is positive, these two are negatives. This positive is a little smaller than the sum of these two, right? There's a little bit more negative area, and that's why we end the function in the negative side. Good. So that seems to make sense for the selection of each of these. So this guy here has to be A. Oops. A, B, and C. Good, good, good. Okay, C. Okay, another fantastic question. I love this kind of question. This is a fantastic exam question. Find the graph of S consists of 3 segments shown, where g of x is equal to the integral from 0 to x of f of t. Find g of 4, and then find g prime of 4. Okay, g of 4, first 4, that's going to be 3 and 4, right? This one's 4. 1, 2, 3, 4. So we want to find the area underneath the curvature starting from 0 to 4. It means that we're going to end up with 2 shapes that we have to find. We want to find the area of this triangle over here. Well, let's break it down into pieces. We have the area of this triangle over here, the area of this triangle over here, and then the area of this rectangle in the middle. Right? One triangle, another triangle, a rectangle, and another triangle. Good. And then these are really simple shapes to have. The area of a triangle is 1/2 base times height. The base is a 1, the height is a 2. Same thing for this one, 1/2 base times height, 1/2 base times height. And this one's just going to be 1 times 2 since it's just a giant rectangle. Right? So find the each one of those 4 shapes, add them together, and that'll be g of 4. Good. Could be good. And what is g prime of 4? Well, remember that g prime must be equal to this guy. It's the f function evaluated at 4. Okay. So this is just going to be 0. Evaluated at 4, 0. Good. Questions, questions, questions? Okay. What about something in the teams? Any questions about how to integrate any of these guys? No questions, no questions. Okay, so I'll just pick a couple. How about number 15?
21. Number 21 looks fine.
Oh, great. We'll get to 21. I wanted to start off with something in the teens. So we'll go to 21 as well. But let's pick something else. Does anybody else have a question of something in the teens? Or the tens? The tens. 11, 13, 15, 17, 19.
I say number 15.
15. Okay, yeah, let's do 15. So let me...
Jose Escobar has a question on 18.
I think I only assigned the odd ones, right? So I want to stick to the odd ones for now. If you guys want to do some extra ones, I'd love that. And we can, make time for those as well. But okay, so let's do number 15 first. So number 15 in Chapter 5 review. So this is Chapter 5 review questions. Has the integral from 1 to 9 of, and then we have square root of u minus 2u squared all over u du. Okay, so what we want to do here is separate this fraction into two separate fractions. The integral from 1 to 9 of root u over u minus 2u squared over u du. Good. Then we want to simplify each one of these. This is the integral from 1 to 9 of u to the 1/2 power divided by u to the 1 power minus, and then here we can already cancel one of these guys, right? This reduces with that to give you a 1. So we can just have a 2u du, right? And all of this is being applied by that du. So this still has over here. Okay, remember that when we have a fraction like this, x to the third, x to the 1, this is x to the 3 minus 1, we subtract them. Right? So this is going to be the integral from 1 to 9 of u to the 1/2 minus 1 power minus 2u du, like this. And so this is going to be equal to the integral from 1 to 9 of u to the negative 1/2 minus 2u du. Good. And now we can apply our antiderivative rules. So we know that this is going to be equal to u to the 1/2 power, negative 1/2 plus 1. Right, so I know there's going to be 1/2, and it's kind of a guess and check situation. I have to think about, I need to find some function whose derivative equals to this, and the constant is 1, so this is going to be u to the positive 1/2 power, right? And if I take the derivative of this, we bring down the 1/2, so I need an extra 2 in there. Minus, and then u to the second power gives me exactly this. Good. Evaluated at from 1 to 9. Good. Any questions about that? Good. So this is going to be equal to 2, and then 9 times 9 to the 1/2 power minus 9 squared.
I have a question.
Yeah.
Like 2 steps before, like where you're at right now.
Yeah.
You did the antiderivative of u, so like you added one instead of taking derivative minus one, right?
Correct.
Yeah, that's it. That's all I want to know.
Okay. Yeah. When we take derivatives, we subtract one from the exponent. So therefore, when we're taking antiderivatives, we add one to the exponent, right?
Okay.
And a lot of it is guessing and checking. You think of a function that might work and then check it, because taking derivatives just always feels more intuitive. So There are some rules, but really a lot of it is just write something down and then take its derivative and confirm that it works. So I wrote this down. Now if I want to take its derivative, I know that in derivatives, you take this exponent, you bring it out in front, then the 2 and the 1/2 cancel, and then you subtract 1 from the exponent, and you get 1/2 minus 1 is equal to negative 1/2, and that's what this is. Good. Okay, so now evaluating it from, u goes from 1 to u goes to 9, then we apply the 9s, right? Wherever there's a u, we replace it with a 9, and then we end up with 2 times 1 to the 1/2 power minus 1 squared. U to the 1/2 power, remember that's the same thing as the square root of 9 minus 9 squared, which is 81, minus 2 times the square root of 1 minus 1. So this is going to be 2 times 3 minus 81 minus 2 minus 1. So that's going to be 6 minus 81 minus 1. So that's going to be negative 75 minus 1 for a final answer of negative 76. Any questions? Questions? No? Okay. All right, so the next one, we had a request for 16, was it?
He does those, I think.
18. There was a request for 18. Was there a request for 17? No? Nobody? Okay, 18 is just as good as 17. Let's try number 18 then. So 18 has y squared 1 plus y squared. Okay, so let's put this one. Okay, so this is a review of chapter 5, number 18. And we had the integrals from, where'd it go? From 0 to 2 of y to the power of 2 square root of 1 plus y to the power of 3 dy. So this is a perfect example to refresh our memories on u substitutions. Okay, so what we're going to do is come up with the perfect u substitution, and that is the hardest part of these questions, coming up with the proper u substitution. So I'm going to let u equal this part here, 1 plus y cubed. Why did I do that? Because from experience, I know that you want to pick something so that when you take its derivative, I want the derivative to be somewhere in my statement. Okay? So if I had let this be my u, its derivative would just be y, and then that would be complicated, right? I mean, I guess I could try and jerry-rig it in there and force it, but it wouldn't be pretty and it's not going to work out well. On the other hand, if I let this be u, its derivative is going to be something to the power of 2, and then that's that guy right there. Good. Okay, so we're going to let u be this part. So I know that when I take this integral, let's go back to black here. So this is going to be some integral, and I know I have this thing in there, and now I know that this is going to be in there, right? The u is going to be that. Okay, but now I also have to think about the derivative with respect to u. So I'm going to take dy of the u function. Good. So that's going to be dy of the 1 plus y cubed. Right? It's dy both sides of this. Good. Okay, so now this, well, this notation is exactly du dy. equals, and now the derivative of this, the derivative of 1 is 0, and the derivative of this is going to be equal to 3y squared. Good. Okay, I'm going to multiply both sides by dy and get that du equals to 3y squared dy, which is right there. The dy, the y squared dy. So I'm going to divide this side by 3 and get that 1/3 du equals to y squared. You know what? Actually, never mind. I don't want to do it that way. Let's go back over here. Okay, so this is my du. Okay, so now I'm going to come back over here, and all I'm going to do is squeeze this over and rewrite this as the square root of u, like that. And then I'm just going to move this on the other side over there, and we had y squared times dy. Good? Okay, now I know that du is equal to this. There has to be a 3 in there. So as long as it's a constant, I can just throw it in there, times a 3, as long as I also balance it out with a 1/3 out here. Right? Because we know that when there's a multiplication of constants, we can always just pull them out. So I can just pull out that 3. And then 3 over 3 is 1, so that doesn't change anything. And now, by doing that little adjustment, I have the perfect combination here that lets me replace my du. Good? Good, good, good. Okay, now let's look at the limits of integration. You know, if I had it my way, if I was, you know, the author of this book, I would force all these limits of integration to keep track of the variable, right? By default, it's assumed that this is the integral with respect to y, so these are limits with respect to y. But when we do a substitution like this, we got to keep track of those guys. So if I don't do anything, I can just continue to say that this is a limit y and a limit y, right? Okay, so I'm going to go ahead and simplify this a little bit, since all of this is now my du. And so this is going to be equal to 1/3 integral of root u du, right? But now it would be a mistake if you just say, oh, well, this goes from 0 to 2 and we're done with that. That doesn't make sense, because this 0 and this 2 refer to a y equal to 0 and a y equal to 2. Good? So we got a couple of choices. We could continue to work with this now, find its antiderivative, and then resubstitute the values back using this little statement, so we can come back to y's and then apply this. We could do it that way. Or the other option is to use this definition to find the new values of the new limits of our integration. Good. So let's do it that way. So when y equals to 0, we get that u is going to be equal to 1 plus 0 cubed. So u equals to 1. Good. And when y equals to 2, then u is going to be equal to 1 plus 2 cubed. 2 cubed is 8, so u equals to 9. Good. So armed with this knowledge, now I'm ready to change the limits of my integration. Let's go back to this color and say that now this is going to be equal to 1/3 the integral as u ranges from 1 to u ranges to 9 of root u du. And now everything matches, right? We had an original statement written all in terms of the variable y. The limits of integration were in terms of y. The functions were in y. We had dy. Everything was y. And then we were able to do a substitution with u and replace a u part of it. We found out its du part of it, and we changed the limits of integration. So now we have a brand new statement that's going to give us the same answer. right? So all of these equal signs are important because we're saying that this equals that, which equals that, which equals this. So now, you know, kind of going back to the original of 0, the integral from 0 to 2 of y squared square root of 1 plus y cubed dy, that one looks ugly. But we're saying that that's equivalent to just finding the integral of this one, which is much easier. 1 to 9 of root u du. Right? That looks much easier to solve. And in fact, this one we can just rewrite as 1/3 the integral from 1 to 9 of u to the 1/2 power du, right? Reinterpreting the square root of u. And now that should be an easy antiderivative. This is going to be 1/3, leaving that alone out there. And then the antiderivative is going to be equal to u to the power of 3/2, right? Because if we subtract 1 from 3/2, we get 1/2. And if we bring this out in front, we get 3/2. We don't want that, so we got to multiply it times its reciprocal. That way, when, you know, guessing and checking, if I bring this out down in front, the two fractions cancel each other out. Subtracting 1 gets me to that guy. Okay, so it's 2/3 u to the power of 3/2, and we want to evaluate this from 1 to 9. Good. So this is going to be equal to 1/3 bracket. Well, in fact, let's pull out that constant. Let's pull out that constant and put it out there. And this is going to be u to the 2 evaluated from 1 to 9. So this is going to be equal to 2 9s bracket, and it's going to be equal to 9 to the power of 3/2 minus 1 to the power of 3/2. Good. This is equal to 2 9s bracket. This is the same thing as the square root of 9 raised to the power of 3. 9 to the 3/2 is the same thing as 9 to the 1/2 power, the whole thing raised to the 3rd power, which is equal to the square root of 9, all of it raised to the 3rd power, which is equal to 3 to the 3rd power, which is equal to 27. Okay, so this is equal to 27 minus, and then the same treatment here. This is 1 to the 3/2 power, that's equal to 1 to the 1/2 power raised to the 3rd power, the square root of 1 raised to the 3rd power, which is 1 to the 3rd power, which is equal to 1. It's a lot of work. We get a 1, get that. Good. And then after a little bit of work, we get that this is going to be 26. 2 times 26 all over 9, or 52 divided by 9. Questions, 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 questions?
Can you scroll down?
Down or up, you mean?
No, I mean down so like we can like, yeah, like that.
Oh, okay.
Okay, quick question.
Yeah.
I never really understood like where you got the 1/3. I mean, I understand everything else, but like the part that where you get the 1/3, that one's confusing. Like,
Okay, so that comes from up here, right? So I first chose my u to be 1 plus y to the 3rd power, and when I take its derivative, I end up with 3 y squared dy. So there's a 3 there.
yeah.
Okay, so that means that when I come up to here, I need to have a 3. So it becomes out of necessity. I want there to be a 3, and as long as it's just a constant, I can make there be a 3 there. I can just pull it out of thin air and stick it in there, a 3, as long as I also balance it out with a divided by 1/3, or multiplied by times 1/3, right? Because this 1/3 and this 3 cancel each other out, right? They're another version of 1. So that's why I now introduce this 1/3 out in front of my integral, because this 3 needed to be there, and that's my du.
Okay.
Okay?
Yeah, thank you.
So all of this, the 3 times the y squared times the dy, all of it as a little package deal becomes my du. And now I have this 1/3 out in front. So 1/3 integral of square root of u du is equivalent to this one, but we have to, be careful with the limits of integration still. Okay. Any other questions about this problem? Number 18. So great example of how we use the substitution property of integrals to simplify things. Right? This original question was really difficult to try and figure out. Find a function whose derivative equals this. That's kind of hard. Really hard to do that. However, by the u substitution, we got to an integral that was really easy to work with. Square root of u. Yeah, we know how to do that. Good. Okay, so this one was 18. Let's go back to this guy. I believe the next request was 21.
Yeah, mine.
Okay, number 21, and now that seems like, again, a perfect application of this substitution property, right? Number 21. So this is, again, Chapter 5 review, number 21. And it is the integral from 0 to 1 on v squared cosine of v cubed dv. Right? Okay. And again, by default, it's assumed, unless they tell you otherwise, it's assumed that the variable of integration here matches. So it's just assumed that this is from v goes to 0 to v goes to 1, though, they often omit that. But if I had it my way, every single integral would have that in there, just to constantly be certain that we have the same variable there. Okay, so now we want to do a u substitution, because this is hard. Think of a function whose derivative equals to this. That's hard, especially because we have a multiplication here, right? We know that if we take the derivative of something, it's going to be hard to think of it. Just kind of the brute force method to just kind of think of what that answer is. So a u substitution seems to work out well, because I can see that if I let u equal to this, its derivative is going to be right there. Good. So we're going to let u equal to v cubed. Good. And now when I take the derivative, du dv, I'm going to end up with 3v squared. Good. So du is equal to 3v squared dv. And the v squared dv is there. Again, it's missing a 3, right? So it's a little unfortunate that both examples both have a 3 there. I don't want you to get the impression that it always has to be a 3. It just so happens that we're dealing with cubes here, and so we have that pattern. Okay, so we're going to come over here, and we're going to change these guys. I'm going to leave my v to 0 and v to 1 as my limits for now. I'm going to rewrite this as cosine of, and then I'm going to replace that with that u substitution, right? So v cubed is u. And then we have this v squared dv here. So I'm going to have to introduce that 3. 3 goes in there, and I balance it out with a 1/3 out there. 1/3 times 3 cancel out, and now that becomes my new du. Du equals to 3v squared dv. So I can simplify all of this saying it's 1/3 integral as v goes from 0 to v goes to 1 on cosine of v, I'm sorry, cosine of u, cosine of u du. Good. Questions? Okay, so now the other way we could do this is to continue to work with this, but keep in mind that that's limits is a v. So something whose derivative is cosine of u, the antiderivative is just going to be sine of u. Right, so one thing we could do is just say, well, let's continue with this. This will be 1/3. The antiderivative of that is just going to be sine of u, evaluated at these limits, which is v goes from 0, v goes to 1. Good. Now, normally we would just plug those in there, and we can find our result then. However, here we have to recognize that this is the variable u, and these are for variables v. So we can come back to this to replace the u with a v again. So this is equal to 1/3 sine of v cubed, right, evaluated from v goes to 0 to v goes to 1. And now we can find our answer as 1/3 sine of 1 cubed minus sine of 0 cubed. Good. Questions? So this is just going to be 1/3 sine of 1 minus sine of 0. Sine of 1, well, we don't know what that is. That's not an easy answer. We can use our calculator to approximate it, but we can just leave it alone. However, sine of 0 is going to be equal to 1. No, sine of 0 is 0. Yes. Sine of 0 is 0. So this becomes 0. And so this is our final answer. Equals to sine of 1 over 3. Right? Remember, by default, these are radians. So 1 radian. Sine of 1 over 3, not 1 degree. Any questions about that? Good. Okay, so one option is to keep the same limits of integration with the same variable that you started with. Just make sure you keep track of them. Then find the antiderivative of this. Keep working with that new letter, in this case a u. Good. And then you use your definition, your description, your substitution to come back to describe your function in terms of the letter v. And now you can use the original limits, right, 1 and 3. What you cannot do is just plug this in there right now, because this is sine of u, and these are in terms of v. So we gotta replace it and rewrite it as a function in terms of the letter that matches the limits of integration. Good. Or, the other option, put a big or, like we did before, what we could do is think about the little subcases, right? When v equals to 0, then u equals to v cubed, then u equals to 0 cubed, which means u equals to 0. And when v equals to 1, then u equals to v cubed, u equals to 1 cubed, so u equals to 1. Good. So using this little thing, the other way we could do this is to say now that this equals to 1/3 integral as u goes from 0, u goes to 1, of cosine of u du. I've changed the limits of integration, right? So now all the letters match. Cosine of u, it's a function of u, du, and the limits of integration have the same variable. It all matches. So this is going to be 1/3 sine of u evaluated from 0 to 1. And now I can just say that this is 1/3 sine of 1 minus sine of 0, which then ends up giving me the same answer. This guy is 0. And so my final answer is still going to be sine of 1 divided by 3. Good. They match. Same one. Same answer. Any questions? Questions? No? No? All right, let's go back to the review. What else we got? Everything else is good. Man, 23 looks scary. So ugly. Tangent to the 4th power, t to the 4th tangent of t all over 2 plus cosine of t. Man, how do we find a function whose derivative equals to that crazy thing? It's such an ugly question so early on in the study of integrals that it should be tripping off alarms that something is weird there. There really isn't anything straightforward about that. So that kind of triggers my thought that maybe it's one of the functions that can be solved by sort of a simple trick or a simple property. And if we pay attention to the limits of integration, we can see what's happening here. We're integrating from negative pi over 4 to positive pi over 4. So if it turns out that this function is odd, then I can find the answer pretty easily, right? Then the answer would just be 0. Good. So check that this function is odd, right? Remember our description of what an odd function is. Right? F of x, the function is odd if f of negative x equals to negative 1 times f of x. So check it. Replace all the input values by negative t and see if the output ends up being negative 1 times f of t. If it's odd, that means the answer is 0. Good. Number 25. Seems like the best thing to do is just to go ahead and FOIL it all out and reduce.
Zeros.
Whoa, what's that?
You got me confused with like the zeros. I thought we were just gonna like change the tan sign and the cosine, but then colon. Like, it confused me. Like, how do you do number 23?
You need to check that this function is odd. Do a test to see that this function is odd. If it's odd, then noting that we have the integrals from negative pi over 4 to positive pi over 4 of an odd function, then we know that the answer should be 0.
Oh, because it all counts out. Oh.
Right, if you think about just like x cubed, if we're integrating from negative 5 to positive 5 on x cubed dx, right, because it's an odd function, I know that this answer will be 0. Right?
Okay.
The area above the x-axis and the area below the x-axis will be equal but opposite, so they cancel out and give you an area of 0.
Thank you, Professor.
Sure. Also notice number 19 has a little tricky thing too. The integral from 1 to 5 of this thing, well, notice that there is a vertical asymptote when t equals to 4, right? When t equals to 4, we have a vertical asymptote, so there is no integral there, right? This is sort of an undefined. Good, no solution, undefined for number 19, because there's a vertical asymptote at t equals to 4. Good, good, good. Okay, that one should be odd. This one, just break it up. FOIL out the numerator, right? Shouldn't be that bad. 1 minus x squared. That's just a trinomial, no big deal. The denominator is x squared. And then break it up into 3 separate fractions. Find the integral of each one separately. That should get you home, right? So number 25 shouldn't be too bad. 27 is another classic u substitution. Luckily, if we let u equal to this part, x squared plus 4x, its derivative will be x plus 2. So we have a great application of a u substitution. That shouldn't be hard either. Good, good, good. Another great application of a u substitution, we have sine pi t times cosine pi t. So if we let u equal to really either one of them, its derivative is found there. So derivative of sine is cosine. So if we let u equal to sine pi t, its derivative will be equal to something that we can use, right? Remember, pi is a constant, so there will be a constant thrown in there that we have to mess with. Otherwise, it should be a fairly easy application. Good. What about 31? If we let u equal to the square root of x, its derivative will be equal to 1 over the square root of x, which is found right there. Good. So we end up with e to the u. Good, 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 good. Does anybody want me to do any one of these? And I'm just kind of pointing out how they get done so that you can, get unstuck if you're stuck there trying to do these. But we don't have time to do every little thing, so I'm just kind of trying to get to the highlights. Good, good. So far we're okay. I think these are all manageable. 33. 33, again, a great application of a u substitution, right? So let u equal to ln cosine. In fact, let's do 33. I've skipped over enough. Let's do 33. So chapter 5 review. Number 33. We have the integral of tan x ln of cosine x dx. Good. Okay, so what I want to do is let u be equal to this part, ln of cosine of x. Good. And so now the derivative, du dx, is going to be equal to 1 over cosine of x times the derivative with respect to x, d dx, of the inside function, right? That's by the chain rule. Derivative of ln of x is equal to 1 over x. And so then the derivative of cosine of x, so we end up with du dx equals to 1 over cosine of x times the derivative of cosine, which is equal to negative sine of x. So I end up with du equals to negative sine x over cosine x, which is in fact tangent. So du equals to negative 1 times tangent of x. Well, lucky for me, there it is, tangent of x. Okay, so now I'm going to come back over here, and I'm going to rewrite this as ln of cosine x times, and then there's this tangent x dx. So this part is just going to be my u, and I almost got everything I need for the tangent. I need an extra negative, right? So I'm going to multiply it by -1 so that I have exactly my du. But then I got to balance it out, so I have to throw in an extra -1 out here. That way those two cancel each other out. And I end up with my new integral, -1 times the integral of u du. Easy as pie. Good. This guy is going to be equal to -1 times u to the 2 power, right? I bring down the 2, I get a power of 1 there, so that's going to be a 2. But if I bring out a 2, there's no constant there, so I have to multiply by 1/2, right? This makes me have that. Good. So I end up with this, and then since this was an indefinite integral here, there was no limits of integration, then we have to think about the fact that this is solved by this function or any other constant. So -u squared over 2 plus a constant ends up being my answer. And then, well, you know, nobody asked me about u. The original question was in terms of x. So it would be nice if we come back and replace that with negative. And then replacing the u gives you an ln of cosine x squared. The whole thing was squared. All over 2 plus some constant, c. Good. Questions, 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 questions? This looks kind of messy. Maybe it would look a little neater if I wrote it as -1/2 out in front. And then, well, there's just no way to not make this messy. This is just messy. Like that, and then that whole thing gets squared plus a constant. Any questions about this one? No? We're good, we're good, we're good. Okay, moving on. I see another great application of u substitutions, right? Because if I let u equal to this denominator, its derivative will involve an x to the 3rd power. There it is, right there. So that should be easy. Same thing for 37, another great application of u substitutions. 39 looks a little trickier. We have this absolute value function that we want to integrate. And what we want to do, what we want to be careful about doing is figuring out the regions that we need. Like, when will this make a difference for this function? So let me tackle number 39. Chapter 5 review. Number 39. So it was the integral from 0 to 3 on the absolute value function x squared minus 4 dx. Okay, so what I want to note is, when is this function positive, when is this function negative? Because in certain places, this absolute value is going to be necessary, right? So, okay, so I'm going to kind of do a little bit of side thinking over here. X squared minus 4, I know that factors as x plus 2 and x minus 2, like that. And if I think about number lines, let's think about a number line that has an x plus 2. So here is 0, here is 1, here is 2, here is 3. Over here is -1, -2. Okay, so the 0, the place where that little product becomes 0 is at -2. So I'll say 0 here. Good. And for any value that's to the right of that number, this little binomial becomes positive, right? So if x becomes a 1, we get a 3. If x is a 2, we get a 4. If x is -1, we still get a positive 1. So the little binomial is always positive in this direction, and it means that it's negative in that direction, right? Any other value that's over here on the number line, like -3, is going to give us a negative answer, just for that little binomial. Okay? So next we think about a little binomial that involves just the number, just the little binomial of x minus 2. Good. So here is -2, -1, 0, 1, 2, and 3. Okay, so the 0 of this little binomial is found at +2. Right? If I let x equal to +2, I get a 0. Any number to the right of that, I'm going to get positive numbers. Any number to the left of that, I'm going to get negative numbers. Good. And finally, now I'm ready to consider what happens when I multiply those two. So if I have an x minus 2, x plus 2, here is -2, here is +2, here's 0. Well, I know that at those 2 points, I'm going to get a 0. Right? This is going to be 0, and this is going to be 0. If I replace the x's, both of them, by a +2, I'm going to get 0. Right? Because this is 0. 0 times 4 is 0. If I replace both of those x's by -1, I'll get -4 times 0, which is 0. Good. So the interesting thing is the other regions. Over here, if I pick x values that are to the right of 2, I'll get 2 positive numbers being multiplied, so I get positives. Between -2 and +2, I'll get a positive times a negative, so I'll get a negative answer. And then below -2, I end up with positive numbers, so I get a negative times a negative. Good. So all this is to let me know that on the number line, whenever I graph this, whenever I'm graphing this x squared plus x squared minus 2, and maybe just kind of thinking about what that graph looks like, you should get the idea that this thing graphs like this. Let's come back, goes up like that, and then here is -2, here is +2. The function itself is going to be negative between those two values. Good. This is x squared minus 4 is that guy. Good, good, good. So it's negative down there. However, the fact that it's the absolute value of means that I'm going to have to make it positive. Good. Okay, so from 0 to 3, here is 3. And let's say here is 0. So I'm going to integrate from 0 to 3. From 0 to 2, the absolute value has an impact. This is normally inside here a negative, but the fact that it's inside the absolute values is going to make it positive. So I need to introduce an extra term of -1 to make it positive. Okay, so let's rewrite what we need. The integral from 0 to 3 of the absolute value of x squared minus 4 absolute value dx is going to be equal to the integral from 0 to 2 of x squared minus 4 dx, and I have to introduce a -1 into there, right? Why is that? Because this is always negative between 0 and 2, right? X squared minus 4 is going to give us negative answers. And I want the absolute value of that, so I know I have to make it positive by multiplying by a -1. Plus the integral from 2 to 3, And in that little section, I know I don't have to do anything. This part automatically gives me a positive answer, so there's nothing to do. Good. Distributing this little minus through, I could distribute that little minus through, or I can leave it on the outside, this little minus 1. And now finding the antiderivatives, I'll end up with 1/3 x to the third power minus 4x, evaluated from 0 to 2. Good. Plus, and then it's going to be the exact same antiderivative here, 1/3 x to the third power minus 4x, evaluated from 2 to 3. Which gives me -1, 1/3 something cubed minus 4 times something minus 1/3 something cubed. Well, okay, what do I want to do? Let's put it in parentheses, I guess. Minus this and this. Minus something minus 4 times something. Okay, so here I want to insert these limits, the 2 and the 0. So 2, plug into each of these. I get 1/3 2 cubed minus 4 times 2 minus, and now it's the 0 plugged into each of these. 0 goes into there, 0 goes into there. That takes care of this part. Good. I still have to deal with this part. I'll just put it right underneath it. Plus, and then I have 1/3 something cubed minus 4 times something minus, and then it's going to be 1/3 something cubed minus 4 times something. And in this case, it'll be the 3 and the 2 that gets plugged in. So 3 goes into there, 2 goes into there. Good, good. Okay, so then being careful here, I have this -1 that applies to this whole thing. So this would be -1, and this would be 2 to the third power is 8, so it's 8/3 minus 8 minus, and that's 0 and that's 0, so that's just -0, plus, and then this is going to be 3 to the third power is 27 divided by 3, that's going to be 18, minus 12 minus 8/3 plus 8. Good. Distributing this minus, I end up with minus 8/3 plus 8 plus 18 minus 12 minus 8/3 plus 8. Minus 8/3 minus 8/3 gets me to minus 16/3 plus, and then 8 plus 8 is 16 minus 4 is positive 4 plus 18 gets you to plus 22. And if we rewrite this with a 3/3, we get to 66 minus 16/3 plus 66/3, which gets you to 50/3. Uh-oh, that's not the right answer. So, what did I do? 50/3, that's the wrong answer. Did anybody catch where I made a mistake? I made a mistake somewhere. Integrating from 0 to 3, absolute value, 4, Two, 2, 0, cancels out, and 2 gives you 8. 2 gives you 8/3 minus becomes plus. And then this one is 3 and 2. 3, 27, 18. 18 and 12. That's 6. Made a mistake right here. Here's my mistake. I blame you guys for not telling me. 3 to the third power is 27. 27 divided by 3 is 9. So not 18. This is 9. Right? This whole thing right here is 9, not 18. So this should be 9. Should be 16. 16 minus 4 is 4. Plus 3 makes it 13. What the heck's happening with this? What? So that makes it 13. 8, 16 minus 4 makes it 4. 4 plus 3, 9 makes it 13. Good. Okay, so then that would make this guy 39. 39 minus 16 gets you 23. 23 over 3. Is that the right answer? Yes, that's the right answer. Cool. 23 over 3. Any questions about that? Gotta be real careful with the arithmetic, right? Easy to make a mistake. Any questions? I hope it's clear on why I had to break it up this way, right? Because it's the area. Here the outputs were negative, and the absolute value indicates that it's got to be positive. So I need to figure out what this area was and make it positive. Right? That's why we threw in that extra minus. Good. Questions, 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 questions? Okay, as usual, I'm overly ambitious as to how much we'll complete. So 39, there's still a few more questions that we can kind of think about in terms of our review. So keep going through the review process. I think I asked you to stop somewhere in the 60s by doing the odds. So spend the weekend working on those, and next week we'll come back and I'll still entertain a little bit of time to answer some of these questions in the 20s and in the 40s, 50s, 60s, the odd ones, and then we'll move on to chapter 7. So on the other hand, if you already did the assignment and you feel happy with it, then don't wait for me, move on. Start reading chapter 7, section 1, and start doing the homework. If you finish that, then move on to section 2, then move on to section 3. All your homework has already been assigned, so it'll make it easier for you if you can move ahead, jump ahead, and stay ahead of me. That way, things will get easier for you. Okay. All right. Okay. Well, this is a good place to stop.